non-regular. We've been taught, you investigated the regular. Well, in the homework, I had you do a non-equilateral triangle. Did anybody cut those out and put them together? Did anybody bring those to class?
I just copied out the Word document.
Oh, so you made one and then just quickly duplicated it, and then how did you get it to...
I just rotated it.
Ah, in the Word document. Did they?
Yeah, they did.
They what?
They tested it.
They tessellated. Anybody else get theirs to tessellate?
I just used GeoGebra.
GeoGebra. Great place to go. Take it and then get a copy of that same one and move it around and see if it will fill the plane. Did it? Does every single triangle, no matter what size or shape, do it?
Yeah.
Obtuse as well as acute, and scalene and isosceles, and why?
Because every triangle adds up to 180.
Every triangle adds up to 180.
So therefore, every triangle has to tessellate.
So if we go back to what we did in Unit 1, where we drew our triangles, and some of you drew obtuse, and some of you drew acute, and some of you did equilateral, and you tore the corners off, right? And what did we do with the corners? The vertices? We place them into a straight line, and the three of them made how much? 180. So if this is angle 1, and this is angle 2, and this is angle 3 of the triangle, we tore those off, and they made 180. So how does that prove they tessellate? That's a straight line.
You can put it in for 360.
I could take those same three and put them down here, right? Extend this here, that's 1. Extend that one down here, this one's 3. Do you see the vertical angles? And this one's 2. And so now I have 6 around that point, and I could go on forever doing that. Does that make sense? If I could draw this so that... Okay, that's supposed to be parallel to that one. If so, then that angle is the same, because if I've got two parallel lines cut by the transversal, these corresponding angles are congruent, right? This one's 2. So that size is the same as that one. So if I took this up here and put it in here, now this is angle 1, right? And this is angle 3 up here. And we could go on and put angle 3 there, and so on, and we just keep building the... So every single triangle will, because of what we learned about in Unit 1. What about non-regular quadrilaterals and pentagons and beyond? In other words, they're not squares, they're not even rectangles. Well, rectangle is non-regular, I guess, and rectangles we know will, right? What about this?
Yes.
Is it tessellatable, I guess? Is that a verb? Does it tessellate? How do we know?
Because they all add up to, or, yeah.
Because angle 1 plus 2 plus 3 plus 4 make 360, we learned in an earlier unit. So I could come to any of these vertices and I could put a angle 1 in there, right? I could put an angle 3 in there and an angle 2 in there, and those would go around that point. And they would, and if you matched corresponding sides, for example, this one here is angle 3, the side between angle 3 and angle 4 is going to be over here, right? I did a, and then up here, this is between 4 and 1, so this one's going to be angle 4 up here. Do you see what I'm saying? So 1, 4, 4, 1, we know that side will match. 3, 4, 3, 4, that side will match, and you just keep building and out it goes, and every single quadrilateral.
So does that mean that if you take a set group of
shapes, no matter what, like they don't have to be the same. If the point where they come together, if all of that adds up to 360, if you kept all those together, they were tessellate.
That's what we're saying with the triangles, and we're saying that with the quadrilaterals. Are you asking about other
So
things?
like if you take any shapes, and as long as the points where they come together, if all of them add up to 360, that makes sense. If I take a square and a pentagon, that kind of thing. Like as
Oh,
long
so
as I
you're-
keep all of them together.
So you're not doing a pure tessellation now, you're taking more than one shape. Yeah, it's got to add to 360. Yep. Good, great observation, Catherine. Well, since regular polygons did not create a tessellation, you know that not every pentagon will. Is there at least one pentagon that will tessellate?
Yes.
Yes, there are many. What types of pentagons tessellate? Prior to 1967, and that's not that long ago, I mean, that was 3 years after I got baptized, so this is modern history here. It was thought that all tessellating pentagons could be classified into 5 types. But that year, Richard B. Kirshner of Johns Hopkins University found 3 more. So making it what? 8 types of 5-sided polygons that will tessellate. Most everyone thought that the problem had been solved. They thought, that's all of them, until in 1975, Marjorie Rice, a San Diego mother of 5, entered the picture. She read an article in Scientific American by Martin Gardner on Kirshner's discovery of those 3 new types of tessellating pentagons. Then she began her own investigations. With no formal training in mathematics beyond high school general math. That means she didn't have algebra or geometry classes. And some of you are saying, mother of 5, when does she have time to read Scientific American? But she was, and she read about it and became intrigued and started playing around, and within a few months discovered a 9th type, and then by 2 years later she had actually discovered 4 more types. And the college and university mathematicians who had been working on this had not been able to do it. This is impressive, people. I don't know if it impresses you, but it tells you what you're capable of doing. And especially in a field like geometry, you think, wow, everything's been discovered that has been discovered. No. And you don't have to be a genius to do it. Or, she didn't have much training. She just had some inclinations to think and discover. I love this story. Here are some of here's her 9th type and her 13th type. Notice they're pentagons. But Catherine, you'll notice right around this vertex, those 3 coming together have to what? Add up to 360. It's got to be, no matter how we do this. Okay? If you're interested in learning more about what she did and how she did it, and how these designations down here determine the type, just Google Marjorie Rice tessellations, and you can get right to her website and see all of the types that she discovered. And great story. Okay, semi-pure involve more than one shape. Remember, pure is just one single shape used over and over and over again. Semi-pure, you can choose more than one shape. Okay? When the same combination of regular polygons meet in the same order at each vertex in a semi-pure tessellation, the tessellation is called semi-regular. By that we mean this. It says they meet in the same order at each vertex. If I take that vertex right there, what shape's this? Octagon. So I have octagon, octagon, square. These are regular, right? Every place I touch a vertex, I find octagon, octagon, square, right? 4-sided, 8-sided, 8-sided. touch it right there, I get 4-sided, 8-sided, 8-sided as I go around that. Okay? We call that a semi-regular. Okay? The way these are designated is you go to a vertex, start with the polygon with the smallest number of sides, and then you can go either clockwise or counterclockwise, and you may use exponents where possible. So this one at the left, since every vertex has a 4-sided and 2 8-sided ones, we go 4.8.8 or 4.8 squared, because these two octagons are in the same, are right together, so we go 4, 8, 8. No matter where we start, there's 4, 8, 8 as we go around. Do you see it? Start at the smallest, go either direction. So, what I'd like you to do is figure out the designations for these two semi-regular tessellations. How about this one? Somebody got it? You can pick any vertex. That one, that one, that one, anywhere. They should have the same designation. What is it? Is it 12, 3, 12? Why not? You got to start with the lowest. So it's going to be 3. Then I can go this way, or I can go this way. Either way, I get 3, 12, 12, or 3, 12 squared. Right? What about this one? Everybody found this one? I could pick this one. Where is the smallest number of sides around that vertex? 3. So I have to start here. 3, does it matter which way we go? No. No. So 3, 4, 6, 4. If I go the other way, it's 3, 4, 6, 4. It doesn't really matter on this one. And even though they're not the same, you can go either direction. Could I put a squared on the 4? Because there's 2 of them. No, we can't. Why not? Because they are not adjacent to each other. Okay, so we have to go 3, 4, 6, 4. We can't go 3, 4 squared 6. That would look totally different. It would still fit around a 360, around a point, but it wouldn't look like this. Okay, notice, we picked, which one did we? We picked this one, but I could pick that one right there, and it's the 3, 4, 6, 4, right? I could come over here and pick this one. 3, 4, 6, 4. It doesn't matter which one we pick. If they all have the same designation, no matter what vertex, that makes them semi-regular. Okay? Alright, if the arrangement at each vertex in a semi-pure tessellation of regular polygons is not the same, then the tessellation is called demi-regular. Let me show you what I mean. On this one right here, if I pick this vertex, what's the designation? 4 to the 4th. Okay? So I've got that. But if I pick this designation, what do I have? 3, 3, 3, 4, 4, right? 3 cubed, 4 squared, right? So that one's different than that one. Do I have any other ones? The what?
There's a big one.
This one? Right there? Here?
Yeah.
Okay, what's that designation? 3, 4, 3 squared, 4. Everybody see what we're,
3, 4.
3, 4, 3 squared 4, or 3, 4, 3 squared 4, depending on which way we go, but it's the same this time. So we've got 1 designation, 2 designations, 3 different designations. Are there more? Or do all vertices fit one of those 3 patterns? The middle of the big square is going to be the 4 to the 4th every time, right? These vertices. These around the center of the are going to be the 3 cubed 4 squared, right? So this one, this one, this one, and this one. The corners of the square are going to be the 3, 4, 3 squared 4. And no matter where you pick, you're either going to be the center of this big square, or you're going to be on the middle of each side, or you're going to be on the vertex of the square, right? Every single point is either the vertex of the square, the center of the square, or the midpoint of one of the sides, isn't it? So those are the only 3. All right, take a minute, see if you can get the, just write them down, get some practice, get you ready for the homework on these other 3. In order to be demi-regular, they have to have at least 2 different designations. They could have 3 or more. Anybody got one for this?
3 squared.
3,
3 12 squared.
3 12 squared, right there. What else? 3 12 3 4. That one could also be named 3 4 3 12. That's a different order, but it's okay to go either direction. You got to start with one of the smaller ones. Okay? Are there any other designations besides those 2? Is that it on that one? Yeah, as you look at it, you're either at the corner of this square here, or you're at the tip of this triangle, right? I think that's the all right. These don't look too fancy, but if you colored them with certain patterns, they'd look way cool, right? How about here? Somebody want to give me a designation they found?
3 6.
3 to the 6th, right here, and there, and there. What else?
3 4, 3 3 4.
3 4 3 3 4 around there.
And that one you can do 3 squared 4 3. Or
That same one.
yeah.
You could do 3 squared 4 3 4 because you started at a 3 and you just squared it. You could, instead of starting at this 3, you could start at one of those 2 3s, and yep, that would be the same designation, just a bit different order. Is there just 2 there? What about here?
You get 3 4 6. Or 3
3
to 4.
to the 4th, 6, right there. 3 to the 4th, 6.
Or you can get 3 6
3
3 6.
6, 3 6.
Or you can do 3 squared 6 squared.
Or you can do
Or you can
3 squared, 6 squared. There's third one, right?
Or you can do, looks like you got 6 cubed.
Or 6 cubed. This has got 4 designations. Everybody see how it works? That's why these are called demi-regular. There are the designations. Okay? This is like your homework. You've got to decide, is it semi-regular or is it demi-regular? If it's semi-regular, there's only going to be 1 designation. If it's demi-regular, you'll find 2 or more designations for them. Anybody have any questions? Let's get started with our understanding of tessellations then.